In today's talk, we'll start with an example which was on one of the homework problems, problem H31, which you probably did for today. The problem is, given this 3x3 table or 3x3 grid, we want to color the squares with two colors, say colors A and B, and we ask how many different ways are there to do this if two colorings are considered the same, if you can rotate one to get to the other. In other words, our symmetry group, our rotation group, is just the rotations R0, R1, R2, and R3. We developed a formula for counting the orbits, which is the number of distinct colorings, and that formula said we just have to add the invariant numbers for these four rotations, R0 plus R1 plus R2 plus R3, and divide by the number of rotations here. That's just 4. So that will give us the total number of orbits, which is the same as what we mean by the total number of colorings. How do we compute R0? Well, we just ask how many colorings are there, because every one of the colorings is fixed by the identity rotation R0. Well, we have two choices for what goes in each square, so there are 2 to the 9th total colorings. And R0 is exactly 2 to the 9th, because every one is fixed by R0. What about R1? How many colorings are fixed by this R1? And I should be a little clearer, what do I mean by R1? R1 is a rotation, say in the clockwise direction, of this square. So what's in this upper left corner would go to the upper right corner. What's in the upper right corner goes down to the lower right corner. From the lower right corner goes to the lower left corner, etc. Things in the upper middle go to the right middle, then to the bottom middle, and then to the left middle. Under any rotation, the color in the center stays the same. So how many colorings are there that stay exactly the same when you apply a rotation of 1 unit, meaning a 90-degree rotation here? Well, to be fixed under R1, we would need whatever color is here to be the same as the color here, here, and here. Because then when we rotate it by 90 degrees clockwise, those stay the same. Similarly, whatever is here has to be the same as whatever is here, and here, and here. And whatever's in the middle, that can be any color we want. So, how many different colorings are there? We have two choices for which colors go, which color goes in all the corners. We have two choices for which color goes in all the middle edge middle squares, and two choices for which color goes right in the middle. In all, we have 2 to the 3rd choices for a coloring that's fixed by the rotation R1. Now, how will we compute R2? Well, if we want a coloring that's fixed under R2, R2 is just a rotation by 180 degrees. We need whatever color is here. When I rotate by 180 degrees, it has to be the same as the color that's here. Whatever color is here has to be the same as the color that's here. Whatever color that's here has to be the same as the color that's here. Whatever color is here has to be the same as the color that's here, and we can have either color in the middle. You'll see we then have two choices for the upper left and lower right squares. They have to be the same as each other, but they could either both be A's or both be B's. We have two choices for the middle squares in the top and bottom row. We have two choices for the middle squares in the left and right row, two choices for these other corner squares, and two choices for the square in the middle. That's in all 2 to the 5th choices for a coloring that's invariant under the rotation R2. Now, I claim R3 is just the same as R1, and that's 2 cubed. That's easy to see by symmetry, since the rotation R3 is just the same as the rotation R1, just in the other direction. So the number of orbits is exactly 2 to the 9th plus 2 cubed plus 2 to the 5th plus 2 cubed, all over 4, and you probably computed that. That's 140. Now I'd like to extend that example a bit. What if we allow reflections as well as rotations, so that our new, what I'll call the symmetry group, these are all the different transformations which, if you can get one coloring by applying one of these transformations from another, we'll consider the same coloring, the colorings the same. So what is the symmetry group? We still have the rotations R0 for the identity rotation, R1, R2, and R3, but we now have these reflections. And what reflections do we have? Well, we could reflect about this line. I'll call that one F1. We could reflect about a vertical line through the middle. I'll call that one F2. But don't forget, we also have a possible reflection about this diagonal. I'll call that F3. And about this diagonal, F4. So our symmetry group will now consist of 8 transformations, F1, F2, F3, and F4. And we want to count the orbits. And I should have said again, we're using 2 colors for our colorings. We want to count the orbits for the colorings. How many are different under where we consider colorings the same if you can apply any of these transformations to get from one to the other. And notice that when I talk about our symmetry group, it really has to be a group. We can't just leave out 2 of these reflections. In order to apply Burnside's lemma, the lemma we developed for actually counting orbits, we need this to be a group. That means it has to be closed under multiplication. If we left out this reflection F3, this would no longer be a group because it wouldn't be closed under multiplication. F3 is just flipping about this diagonal axis, is really the same as doing a rotation R1 and then flipping about the horizontal axis F1. So if we left some of these out, it would no longer be a group. I'll leave it to you to check that if we multiply any of these transformations together, we get other transformations that are within the group. And what do we mean by multiply them? That means compose them. Do one first, then do another. How are we going to count the orbits? Well, the number of orbits now will just be the average of, in this case it's 1/8 because this group has 8 transformations in it. It'll be the average of the invariant numbers, R0 plus R1 plus R2 plus R3 plus R4 plus, sorry, I said that badly. We don't have an R4. We now have to add F1 plus F2 plus F3 plus F4, where these little f's are just the invariant numbers for the reflections, capital F1, F2, F3, and F4. And of course, the problem is just the same as the previous one in that we know that R0 is 2 to the 9th, R1 is, what is that, would be 2 cubed, R2 was 2 to the 5th, R3 was 2 cubed again. But what is F1? How many colorings using 2 colors are invariant under a flip under a reflection, I should say, or flip across this axis, the horizontal axis through the middle? Well, whatever color we put here would have to match the color here. Whatever color we put here has to match the color here. Whatever color we put here has to match the color here. And we can put any color here, here, and here. So how many ways can we choose a coloring that's invariant? We can choose one color for this square and this square. We can choose, that gives us 2 choices. We choose a color for this and this, 2 more. So we multiply 2 times 2. 2 choices for these squares, so times 2 again, times 2 choices here, 2 choices here, and 2 choices here. We end up with 2 to the 6th colorings that are invariant under this reflection. And here's the neat thing. A similar argument will tell us F2 is also 2 to the 6th. And even though F3 and F4 are reflections across a diagonal axis, it's easy to convince yourself that you have the exact same number, 2 to the 6th. 2 to the 6th colorings, which are invariant under those reflections as well. And so what is the total number of orbits? This is just 1/8 times, then we'll have 2 to the 9th plus 2 cubed, plus 2 to the 5th plus 2 cubed, and then I'll have 4 2 to the 6's, 4 times 2 to the 6. And when you compute all of that, you get 104.